Hello everyone, my name is Mayuri Sritharan and I will be sharing my research on two-dimensional material-based negative capacitance field effect transistors for ultra-scaled low-power devices. The field effect transistor, or FET, is a three-terminal device that uses semiconductor physics to switch electrical signals under an applied electric field. The motivation to scale down the size of the FET has been crucial for producing high-performing integrated circuits by increasing the overall density of transistors that can fit on a single chip. However, since classical semiconductor technology is inhibited by the switching limit, there's a clear incentive to find alternative transistor technologies. One such technology is the negative capacitance field effect transistor, also known as the NC-FET, which contains a ferroelectric layer. Ferroelectric materials display nonlinear hysteresis to an applied electric field. These materials allow transistors to overcome the classical switching limit through polarization switching within the ferroelectric layer, a phenomenon known as negative capacitance. This phenomenon makes NC-FET devices especially promising for low-power electronic devices, and thus I will be investigating these devices for ultra-scaled energy-efficient electronics. Currently, my research focuses on simulating a field effect transistor using a two-dimensional or 2D nanomaterial as the transistor channel. 2D nanomaterials have generated great interest and have been projected to surpass the scaling limits that face bulk field effect transistors due to their exceptional electronic and mechanical properties. Within the 2D material family, 4 materials have been experimentally shown to form natively compatible oxide layers with high dielectric constants. These materials belong to the transition metal dichalcogenide family and constitute of a single zirconium or hafnium atom and 2 sulfur or selenium atoms. The presence of a defect-free high dielectric oxide layer can help scale down both the transistor size and the operation voltage, making these materials especially promising candidates for ultra-scaled FETs. Thus, before I simulate my NC-FET device, I will be optimizing my 2D material-based FET using these 4 materials to isolate the best performing material at ultra-scale channel lengths. The simulation methodology has 2 main stages. In the first stage, I will use density functional theory, or DFT, to model the electronic properties such as the band gap and dielectric of the 2D materials. In the second stage, I will model the quantum transport of the charge carriers in the transistor. This is done by solving the non-equilibrium Green's function, or NEGF method, self-consistently with the Poisson's equation to determine the channel charge, current, and potential. The main goals of my research are first, to realize a highly accurate 2D material-based FET simulator that can be extended to an NC-FET simulator. Second, to isolate a single material within the high-K compatible family that performs best at ultra-scale channel lengths. Third, to have my tools and research as a key deliverable for other researchers and engineers to develop next-generation energy-efficient electronics. Finally, I would like to acknowledge the Waterloo Institute for Nanotechnology, University of Waterloo, and the Ontario government for funding my research. Thank you for listening to my presentation.